Okay, thanks, Rick. Yes, today I'm going to talk on this feasibility of detecting quantum delocalization effects on gravitational redshift in optical clocks, and our paper has been on archive. This is a joint work with Maximilian Locke and Misha Woods. Okay, so here is the motivation of our work. Till now, several different quantum gravity theories have been proposed to unify quantum and gravity. And here are some examples that we are aware of. However, most of these examples are still in the theoretical stage, and we still expect more experiments to justify this theories by detecting quantum gravitational effect. Okay. And so recently, Kandelova and my other co-authors, they proposed a protocol that could potentially observe a discrepancy of relativistic time dilation between the quantum case and the classical case. And in their work, they consider a moving quantum clock with the clock and kinematic degrees of freedom in the low velocity and flat space limit. And for an idealized moving quantum clock, they consider if this clock starts with a Gaussian wave packet in the kinematic degree of freedom, then the clock will output a measured time identical to the classical proper time. And if we consider the kinematic degree of freedom of the moving quantum clock is either in a spatial quantum superposition or in a spatial classical mixture of two Gaussian wave packages. And the wave packages, they have a displacement of delta x, and the probability to get one is lambda. And then after a free fall, there will be a discrepancy T coherence between the time dilation of the quantum superposition, which is T superposition, and that of the classical mixture, which is T mixture. And the scale of this discrepancy is roughly 10 to the minus 16 seconds for 1 second of measuring time. And the state-of-art relative accuracy of an atomic clock is 10 to the minus 18. So that means the discrepancy is potentially detectable. However, the previous work by Kandelova and my co-authors is based on free-falling clocks, and nowadays the most accurate atomic clocks are realized by confined atoms. So people may ask how to realize their protocol in a real experiment with a confined atomic clock, and does the noise do harm to the discrepancy? And this is what we want to answer in this work. We show that this discrepancy remains possibly detectable in a confined atomic clock model, and we also propose a method to realize a protocol and detect the discrepancy based on confined optical lattice clock. And we also analyze some possible noises such as amplitude damping, phase damping, and diffusion noise, and provide some feasible region on the noise parameter in order to detect this discrepancy. Okay, so we will go dive into our model. So our theoretical model is adapted from Zeich's model. We consider a point-like we consider a point-like particle with a clock degree of freedom, and we denote the clock degree of freedom by hc, and the kinematic degree of freedom we denote that freedom by k in this gravitational field. And this is the relativistic Hamiltonian in the laboratory frame, and we assume that the metric we are dealing with is static and the gravitational field is weak, so that we can apply the post-Newtonian approximation, which is given by this metric. And then we can expand the lab frame Hamiltonian in the low velocity and weak field limit. And furthermore, because our particle has a inner clock Hamiltonian, has an inner clock degree of freedom, so we can replace we can replace this mc square by mc square plus the Hamiltonian of the inner degree, and we can split the Hamiltonian into the kinematic Hamiltonian HK and the clock Hamiltonian HC. And we also assume that the atomic clock is subject to some potential U in the lab frame. So we furthermore add some U to our Hamiltonian. So as a result, we will get this Hamiltonian. Here we have written down all the terms that will contribute to our final result. Okay, so the evolution of the system and with dissipation considered can be analyzed by the Lindblad equation because the clock degrees of freedom have much longer lifetime than the kinematic degree of freedom in an atomic clock. We can consider the decoherence only via the kinematic degrees of freedom. And in that case, the equation can be solved by the perturbation theory. Here, this HC and HK in this red frame correspond to the unperturbed Hamiltonian of the clock and kinematic degree of freedom. And those terms in blue corresponds to the perturbative Hamiltonian. And the initial state, it is disentangled between the clock and kinematic degrees of freedom. But after evolution, because these blue terms, these freedoms will become entangled. So the kinematic part will come into the clock parts. Okay, so the clock degree of freedom of an atomic clock is usually described by a two-level system, and this atomic clock it works as follows. It compares the frequency omega naught of the atom transition and also the frequency of a very stable laser, and by stable the laser frequency to the atomic transition frequency, we can use the laser to generate very high quality time signals. And this comparison between those frequencies is via the Ramsey experiment usually. And these Ramsey experiments will produce the Ramsey fringes, which is shown on the right. So the laser frequency and the transition frequency, they coincide at the center of the fringe. And when the atom is still and in a flat space, and the contrast of the fringe is related to the accuracy of the experiment. So when the atom is moving in a curved space, by solving the Lindblad equation using the perturbation theory, we show that the relativistic effect will shift the center of the fringe and will also decrease the contrast of the fringes. So we compute this result by perturbation theory, and these are the lowest order shift up to the center frequency as a contrast. Okay, and now suppose we use two different atomic clocks. One prepares the spatial quantum superposition of two Gaussian states as the initial kinematic state of the clock, and another prepares the spatial classical mixture as the initial state. So these two clocks will give different results, and their difference is considered the discrepancy between the relativistic time dilation of the quantum superposition and the classical mixture. And now we give the discrepancy and the corresponding variance of the discrepancy of the atomic clock. And this frequency and variance are given by this delta, and this delta are given by the I1 and I2 parameter we given in the previous slide. So now we have the theoretical prediction for the shift and the variance. We consider the possibility to detect the discrepancy in an optical lattice clock. So an optical lattice clock relies on the optical potential to confine the atoms. The optical potential depends on the electronic state, and for a specific electronic state n, this optical potential will also is also a function of the polarizability alpha, and the laser frequency omega, and the polarization of the laser p. So a standing wave of the optical field will give a optical lattice, which is shown on the right-hand side of the figure. So for an optical lattice clock, these atoms are usually confined by very deep optical lattice aligned parallel to the gravity, and in this case, we can expand the optical potential near the balanced point and apply the harmonic oscillator approximation. So in that case, we will use the coherent state for the Gaussian states, because these are the most classical choice of the state, in the sense that they have non-negative Wigner function, and also this coherent state can be prepared rather easily by a displacement of the ground state. And now how do we prepare this coherent state or superposition of coherent states? Well, this can be resolved by the so-called state-dependent optical lattice. So consider we prepare the atom in a superposition of two different electronic states, and and these two electronic states are more sensitive to lasers with different polarizations. And in that case, we can displace, we can use optical lattice formed by two standing waves with different polarizations, and we can displace these two optical lattices, and we will obtain a spatial superposition of the atom. This is shown by the picture on the right. So this method can be used to prepare the superposition and the mixture of the Gaussian states. Okay, now we introduce our protocol more. So for timekeeping, an atom must have two very stable states, and this it has two very stable states, and the transition between these two very stable states are used for the frequency comparison. And for this reason, we usually consider, for example, strontium 87 or magnesium 24 atoms. And in order to detect the discrepancy, we additionally need to prepare the quantum superposition or the classical mixture of two kinematic coherent states, and that needs a state-dependent optical lattice, and therefore we have to require the atom to have some more energy structures. For example, energy structure like this. So in this diagram, the colors of the line indicates the wavelength of the transition, and the width of the lines indicates the strength of the transition. And we see, in addition to two very stable states for the clock transition, we also need two meta-stable states and two unstable states for the state-dependent optical lattice. Okay, so here is a summary of our protocol. So because usually the Ramsey experiment part is very well studied, so we mainly focus on how do we prepare the initial state. So we want to prepare either the quantum superposition of two coherent states, which corresponds to the left part, and this is the state we want to prepare, or we want to prepare the classical mixture of these two states, which corresponds to the right part of the protocol, and this is the state we want to prepare. Okay, now keep this two states in mind, I will explain how we prepare them each step, steps by step. So first, consider the atomic state is prepared in the very stable state S1. This can be achieved by the so-called spin polarization. And then we apply, we excite the state to the metastable state M1. And then we use a laser to induce the transition between these two metastable states, M1 and M2, and prepares a superposition of both states. Now we use these two states to perform the state-dependent optical lattice, and with the state-dependent optical lattice, we create an entangled state between the electronic state and the kinematic degree, the kinematic state. Okay, now if we want to get the spatial superposition, we again induce the transition between M1 and M2, and we will obtain this M1 alpha plus minus alpha and M2 alpha minus alpha state. Okay, so now we further excite the M1 state to the unstable state U1, which we get this state, and because this state is unstable, it will quickly decay to S1 spontaneously, and we obtain S1 alpha plus minus alpha state. And the M2 state will be abandoned by electron shelving. That is, we apply a laser to let it jump up to some unstable state, and it quickly fall back to itself and repeatedly. And the momentum it gains within this procedure will burst it out of the lattice, and we just clear it out of the lattice. And if we want to obtain the spatial mixture, we first excite this M1 state to this U1 state and wait for its decay. And then we excite this M2 state to this U1 state and wait for its decay again. And that will result in a mixture of this alpha and minus alpha state. And after we get the quantum superposition and the classical mixture, we induce the clock transition in the optical lattice. And then we we perform the Euro-Ramsey experiment. The measurement in the Ramsey experiment will be done by the electron shelving with this unstable state. Okay, so now in conclusion, we summarize our experimental protocol again. We first use spin polarization to prepare S1 state, and then translate it to M1 state, and then a Ramsey transition prepares the superposition of those two, and a state-dependent optical lattice prepares this state, and then if we want a superposition in the end, we will use a Ramsey transition again to prepare this state, and electron shelving and spontaneous decay to get this state. Otherwise, if we want classical mixture, we again use the optical transition and spontaneous decay to get this state. And finally, we will perform the Euro-Ramsey experiment on those two states to obtain the Ramsey fringes and to get the frequency. Okay, so here is the energy diagram of magnesium-24, and I will explain how to use this atom. So in this case, this 1s0 and 3p0 state will be used as stable state. This 3p0 and 3p2 will be used as metastable state, and this 1p1 and 1p1 and this 3p1 are used as unstable states, and due to the overuse of 3p0 state, an additional cleaning procedure by electron shelving must be performed to clean this 3p0 state after the initial state preparation. And this transition will be used as the clock transition, and all the transitions between this P states are realized by Raman transition. Okay, and the spontaneous decay is realized by this by this transition. Okay, so this is how we achieve it with magnesium-24, and this is our numeric result for magnesium-24 state, which with magic wavelength and at 468 nanometers. So this blue line corresponds to the discrepancy versus the displacement between two Gaussian states, and so it means we require a relative accuracy of 10 to the minus 19 to detect this discrepancy, and this red line corresponds to the contrast, to the decrease of the contrast versus the displacements between the two Gaussian states. And from this result, we see that the discrepancy remains large enough, while the decrease of the contrast is tolerable. So this discrepancy seems possible to be detected in the next generation optical lattice clock. And we also consider some decoherence. So we found that phase damping does no harm to our protocol. Sorry. So it's almost done. So I just say the conclusion. So as a conclusion, it's possible to conduct this real experiment, and our experiment seems to be robust against the noise. That's sorry for the delay. So this is our main conclusion.
Nice, amazing. Thank you so much. Unfortunately, we're not gonna have time for questions. We're already running a little bit late, but thanks a lot for the presentation.